Welcome to the afternoon class of EALE, or EALE. We are doing a talk on the device model and I2C with Michael Opdenacker from Bootlin, formerly Free Electrons. A couple things here. Of course, slides, of course, are still on the cm-eale.org website, same as before, as are all the code pieces and so on and so forth. And for those of you who didn't notice, I was actually handing out one of these DigiKey rulers to people who ask questions. So only one per person, but if you do ask questions, we do have prizes for people as we go through. So otherwise, I will hand it over to Michael. Oh, other than we have a question.
Michael, what's your favorite color?
I think we're going to limit it to technical questions during the actual talk. Yeah, that's right. You already got it. Okay, you have a real question?
I don't know, maybe it's Googleable, so you don't have to answer, but why did Free Electrons change the name?
Well, quickly, we had a trademark dispute with a company in France that's called Free. And while they don't like, to keep their trademark distinctive, they systematically fight any trademark in France that has free inside. Like Free Girl was a t-shirt trademark, and they lost their mark as well. So as we had like little chance to win the trial, like we proactively changed the name and to reduce the the damages that we may get in court. Fortunately, eventually we had a good lawyer, quite aggressive, let's say, and who incited Free to actually sign an agreement with us. And thanks to this agreement, we'll be able to keep the domain name freeelectrons.com forever as a redirection. But at least all the materials, all the links in forums won't be lost. So that's relatively good news. So that's the only change. The company stays the same. It's Bootlin now instead of Free Electrons. And I hope we hope we can like stay focused on the cool stuff and not the legal stuff anymore. Thank you for the question. So trademarks are complex. I expected issues to come from the US, but actually they came from Europe. So the US is not as bad as it looks in terms of litigations. Yeah. So let's get back to technical stuff. Otherwise, I'll get in trouble. So the first thing before moving to device drivers, it's very important to start talking about the way the kernel abstracts drivers, but also connects them to devices, and we'll see that this is done through bus abstraction. And the good news about this is that this is universal. All the we're going to talk about I2C, SPI, but all the devices are managed in the same way for all subsystems. You'll see the same code organization, and it's really wonderful that a community organized in a bazaar style managed to come up with something so consistent across all subsystems with different maintainers. I'm really amazed. So why do we need the device model? Typically for the same device on all platforms, you want to use the same device driver everywhere, whatever the architecture or whatever the controllers that are actually controlling the bus, driving the buses, which could be completely different from one platform to another. Each system on chip has its own accelerator, its own controller. So we still want to use the same device driver, of course. Of course, also you want to have one driver being able to support multiple devices of the same kind. And you'll see how important this is. In some examples, like basic device driver development examples you find on the internet, you'll see a character driver, basic character driver, but this is just driving one device. You want to be able to, of course, have like tens of potentially multiple devices of the same type. All this requires a clean organization of the code with device drivers clearly split from the device controllers, and also the hardware description for the device should be clearly separate as well. I mean, outside of the drivers. So now let's talk about how this integrates in the kernel code. So from the user space application perspective, you have a program that is going to read and write, read from a device, write to a device. And it's going to do that through the system call interface on the files in /dev. Then this goes through a framework, typically, for example, the ALSA framework for sound, video for Linux for video, and things like that. It's a framework that takes care of implementing all the hooks, all the IOCTLs, for example, or some standard functions that all devices will expose to the user. And a framework guarantees that all devices are exposed in the same way. And that's nice, because then your applications don't need to know what exact device they have. That's what makes Linux portable. And then the driver, so the framework will eventually invoke the appropriate hooks that are implemented for each device type by the driver. And then inside the driver, you'll see that it will actually invoke the bus, take advantage of the bus infrastructure to actually talk to the device, like get its interrupt number, allocate yes to find addresses and things like that, or directly to communicate with the device. And then, of course, you access the hardware. So first, here you have two aspects. The first aspect is the framework that allows the driver to expose the hardware in a generic way that doesn't depend on the exact device that you have. And the bus infrastructure that allows to detect the devices and communicate with them. So we first focus on this part, the bus infrastructure. And we'll talk about like declaring device drivers, declaring devices, and things like that. The device model is organized around three types of structures, which are important. The first type is the bus type structure, which represents one type of bus. So each bus implements one structure of this kind, like USB, PCI, I2C, SPI, all of them are declared a bus structure. Then you have a structure dedicated for drivers. It's called device driver, allowing to represent one driver, supporting a certain set of devices on the bus. And last but not least, the device structure, which represents one device connected to a bus, detected by a bus. Actually, if you look at the kernel code, you will see, depending on the buses, you'll see different structure names. It's just because the kernel will actually implement specialized structures. So inheriting in some way, typically embedding a device structure, for example, plus inside the structure containing all other fields, or having this struct device as a member of the main structure. So that's the case for device driver and struct device, and also for the bus type, that's the same too. So we will start by an example, which is the USB, the bus driver, the USB, yes, USB, for example. So you probably know this bus driver, if you watch the same cartoons as I did. So let's take the USB example. It's implemented in a code in driver's USB core. And I'm supposed to talk about I2C, but it's nice to see several examples and really confirm that you have the same code organization and the same concepts that are used everywhere, which really helps in real life when you want to understand and create device drivers. So driver's USB core will declare and register the bus type structure for USB. We'll provide an API to register and implement adapter drivers, so USB controller drivers. that will be able to detect the connected devices and allow to communicate with them. So depending on the SoC that you have a datasheet for the USB controller, and that driver knows what to do to be able, what register to read, knows what to do to detect the devices on the USB bus. We'll also implement a mechanism to match device drivers against the devices detected by adapter drivers. Don't be afraid, it's quite dense, but we have a list of examples. And we'll also define driver and device-specific structures, as I told you. So here, in this case, it's called USB driver for USB device drivers, and USB interface for USB devices. So what we want to have in this case is, well, typically two identical or compatible devices, namely USB 1 and USB 2, which are on two different buses, as you can see, driven by two different controllers. Hence, they have like two different drivers. Sorry, these are two, but just USB 1 and USB buses that contain identical devices, like Dev 1 and Dev 3, connected to different buses, but still managed by the same device driver, even though they are connected to different buses and different controllers. That's what we want to have. That's the same for USB device driver 2 and Dev 4. No, sorry, Dev 4 is the only one. And Dev 2 and Dev 5 are driven by USB device driver 3. That's how that's what we want to implement. So device drivers, the first thing they need to do, in the case of USB typically, but for all buses that I've seen at least, you have to do that, is first to register the devices you support, either by a list of vendor ID and product IDs or by name sometimes. In the case of USB, typically you have some macros to declare some vendor ID and product IDs. You can also match by USB device class, of course, that will work. So that information will be used to match some information that will be available in the devices as well. In USB, each device will have a vendor ID and product ID that the controller will detect, and therefore USB core will be able to match that information from plugged-in devices with the information in drivers, and know that this driver is in charge of such device. So it's called there's a macro called module device table that stores this information in the .ko file that we've seen yesterday. So the ko file is like a container for not only for the code for the module, but also some metadata, the license, but also the compatible devices. Then the next step is to declare a structure, a driver type of structure. Here it's a USB driver, as I told you. So that's yeah. So this continues from this source file in the latest main line. So here we declare a USB driver structure containing a name. I think it's mandatory, and then some functions: probe disconnect, suspend and resume, and edit table functions. Probe is going to be called every time a matching device is found. So probing is supposed to initialize the device, get the device ready to be used, expose it to the right framework and things like that. We'll see that in detail anyway. Disconnect is when you remove the device. So you have like to garbage collect. I mean, you have to clean up everything you registered so that the system is in clean state and memory is reclaimed. You also have hooks for power management. So when typical power management here is suspend and resume. So typically when the device goes, there's a system-wide call for suspending to RAM. Then you can do something before that. So the kernel will go through all the devices and will invoke all the suspend hooks for all the devices. So here you typically can get some device registers, copy them to RAM so that you actually keep them, so that when you resume, you can copy them back from RAM to the device. RAM being kept during suspend, of course. ID table is the table of supported devices that I've just shown you. So you see it's quite simple, a name, a few hooks for different events, and a table of supported devices. And so you remember from yesterday that a device driver file is essentially, at the end at least, you can see an init and exit function. So at module init time, this gets called. Module exit, when you exit or remove the module, the exit function gets called as well. So here, essentially, the only thing we do here is just, we don't know about the existing devices yet. For the moment, we just have to declare the driver, and the matching will happen later. And then when matching happens, then probe will be called for each supported device. So here we just use a function provided by the USB code. It's called USB register, registering the driver structure with USB register, and there's USB deregister at remove time, at exit time, I should say. Otherwise, that's getting confusing. And actually, if you look at the real code, there's a macro that's called module USB driver. It just does that. Taking this driver structure, the pointer to the driver structure, just the driver, actually I think it's the structure name, and then generates this code instantiating the right structure here. Most of the device drivers don't do anything special in init and exit, and therefore this code can just be replaced by module USB driver. The place where you do special things is usually in the probe functions, in the remove functions. That's where you initialize each device and get it ready to be used by user space. So, yeah, so in practice, you will see module USB driver or module I2C driver in most drivers that have been updated to take advantage of that. So now, what are we supposed to do in the probe function? So probe is, again, called for each newly detected device, newly matched device. So the first thing you do is initialize the device, like send write to its registers, get it ready to run, to put it in the proper condition to be ready to serve user space requests. Then prepare driver work, the allocations and things like that, and the registrations that the driver will need to implement its functionality and expose the device to a framework. So typically, as I will show in the examples, you allocate a structure for a suitable framework for like a network structure for a network device. You will allocate memory, typically to allocate the. Or again, yes, I'll allocate memory for your own data structures, per device structures, like for each new device you want to store and keep track of information about it, and therefore you will allocate memory for that as well, unless you have some space in the framework structure for your own stuff, for private data. I see a question. Wait. There's a 5 seconds latency.
On a multi-core system, is the probe called serialized, or those actually can happen all at once in the system?
I think they can happen all at once. Obviously, there's this mechanism so that you don't probe the same device twice. So there must be locking to avoid that. But I don't see any problem like probing 2 devices on 2 different cores. That should be working.
I'm pretty sure there's a lock.
Yeah. Another question?
Hi, I'd like to understand how much of this is for the driver for the USB interface on my device I'm adding to my USB network, and how much of this is for the rest of the device that I happen to implement using that USB interface. So is this more than one level of driver? Am I adapting the driver that came with the USB chip that I put on my peripheral. I'd like to better understand where those two come together.
You mean when you have like multiple functionality on the USB device, or?
Say I'm creating my own peripheral. I'm gonna buy some USB driver chip or a USB chip to put into my device, but then my device has its own functionality. And I'm not sure in what you've described so far how much of this is for creating the driver for that USB chip that I've selected, or how much of this gets into the specific functionality of the device peripheral device I'm implementing using that USB chip.
Okay. True.
I can probably help
Yeah.
with it. Yeah, no,
Yeah, sure.
I get it. I get this question a lot, actually.
Okay.
The thing to understand with the Linux driver model is it's tiered. So what you're describing there is perhaps the host controller for USB on one side, the client or device side chip on the other side. What he's talking about is largely is the driver that's beyond that, basically. And so it depends on exactly what you're working on, but the reality is that there's a driver at each one of those levels. Okay, and so the way the driver model basically works is if you go through sys devices and then you start walking down through the directories, you actually get through all the devices that ultimately get you to the thing you're talking about. Each one of those has a probe function. Each one of those deals with that one device, and you don't have to worry about everything between you and the rest of the kernel. That's handled by the next driver up, and so on and so forth.
Sounds like we're building on top of that. It sounds like we're building on top of that USB interface driver to create the peripheral driver for my lamp or my Wi-Fi adapter or whatever.
True.
Yeah.
So then you need to know how to communicate with the device, like, but only specific stuff to that device, like triggering the MA, or sending the the USB request blocks to it, and only what it expects. You don't have to worry about the controller.
Maybe there's a follow-up question to that, but similar, I guess you could apply it to USB, but if you had a SPI driver that basically just allowed you to communicate to a SPI device, not necessarily any specific SPI device, but then if I implement my own, if I add my own SPI device,
yeah,
can I leverage the base SPI driver and abstract that communication and then just implement my functions, or does it have to be for example, a 7-segment display? Am I writing a driver for the 7-seg with SPI, or is it just the 7-seg and then that uses the SPI driver that already exists?
Yeah.
Okay.
Yeah, you have two cases. You can rely on existing ones and extend them, or just take the basic communication routines that are provided by the SPI bus to communicate with your device and do your own stuff.
It's like on a USB mouse. I'm assuming there's a driver for a mouse.
Oh, well, you don't have anything to do as if it's a standard human HID device. There's a driver for that.
Is that driver also the same driver for USB, or are they kind of tiered, like you said? There's
it's
two
different. The way I'm talking about, like when we talk about the USB driver, at least in those slides, it's the USB bus driver.
And then the HID driver uses the USB driver?
Right. Yeah,
Okay.
the USB core, that's how we call it in the Linux world. So it uses those functions. So effectively, it's not so nice to say USB driver. It's like a bus kind of bus driver, or it's a bit confusing.
So are you talking about a USB driver or the USB bus driver?
USB
right now?
Device driver.
Okay, so this is some other device, not necessarily the USB hub driver.
No.
Okay.
Did you have any other question?
Yeah, I was just wondering, what was the event that causes probe to execute? Is that the bus driver that ends up?
Yeah, the bus driver will match. So the actual event in the USB case there can be two origins. Like either you plug in a new device and the driver is already there, and therefore, or it doesn't need to be there. It could be actually there's a mechanism called UDEV to detect to react to events and therefore load the matching driver. So insert a new device, USB device. the USB core will read the product ID, vendor ID, and class typically. We'll know that the device is there. The second step would be, if the driver is not loaded yet, you would then send an event to user space to UDEV, and UDEV has some rules. Well, there are some, thanks to the device ID, product IDs, and thanks to this information, which when you compile the kernel is turned into module.aliases, you can run mod probe with a string. I probably should show that at this to answer this question. Oops. No, yes. Oops, my mistake. Well, never mind. Don't care. Oops, sorry. Type too fast. For example, here, that's an excerpt of module.alias. This ASICs driver, which is a USB to Ethernet device driver, is going to be loaded for any vendor ID that's this, and product ID this, and all the other ones that it supports. And this matches the information in the device driver, the module device table. And therefore, the Linux kernel, the hot plug system will actually, when a new device is found, will encode the vendor ID, product ID, device class, device subclass, etc. All this in one string. You get this string in UDEV through an environment variable, I think. And then you just mod probe the raw string that you receive from the kernel. And thanks to those aliases and this pattern matching, you eventually, when you mod probe this, you end up loading the ASICs driver if it's not loaded yet. So once this is done, then you have both the devices and drivers, and then the matching can be done by the USB core. And for each detected device, then probe will be called. This also happens if you don't have if you already have the devices, but you don't have a mechanism to load the drivers automatically, and you just load them manually, like when you work on the device driver. You do int mod, and that's when the matching happens. Before that, you had the devices, but no matching device driver. So the matching happens also at module loading time. And similarly, when you remove the module, the experimental module that you're making, this is detected, and the probe routines will be called for each device that was taken care of by the driver.
Does the probe function do any filtering? So
not as far as I know. Like
past a device and it's not really the appropriate device?
No, I think that's a driver issue if you have like devices that are not supported by your driver.
That's checked in the probe function, I believe.
All right.
Yeah, the probe function checks whether or not it actually can deal with the device or not, I believe.
You could do that in a probe. Okay.
You can, yeah, you can, and then you just say this is not my device in the return code from the
but
probe.
It shouldn't be called in the first place, though.
It shouldn't have. That's right. But yeah.
Oh yes. They could do that if you want, but in the normal case, the checks are already done ahead of time by the bus driver. So, yes, back to the probe routine. We will see that in an example. You allocate memory, you map IO memory to be able to access registers, which are at physical addresses. You need a virtual address to access them. Register the interrupts. You do all the work to get the device ready to respond to user space requests. And then when everything is ready, that's important, you can register the new device to the framework. Some people make mistakes register the framework, the device to the framework too early, and this is a potential risk of race condition. Imagine the device is registered but not completely ready to service user space requests yet. Then you could be in trouble, like applications start accessing the device and it's not ready yet, so you could have bugs and race conditions because of that. So make sure you do that when you're completely done getting the device ready to use, like if you have like control characters or instructions or registers to write to get the device ready, make sure this is done before registering, exposing the device and its functionality to user space. So at driver loading time now, what happens? First, you have the USB drivers loading time. They have multiple drivers here. So when the kernel boots, you will first load the USB core. That's the first thing you need to do. It can be a module. It doesn't need to be built-in. Then you will load the controller driver that will register itself to the USB core with the USB add a host controller device function. Then it's time for the device driver to load, and it will register itself to the USB core and the associated devices. It's one of the pieces of information that you have in the device table. And now the USB core knows the association between the vendor and product IDs that are supported by that device driver, and and the USB device, the structure provided by that driver. So the probe and remove, suspend and resume, all the functions that are provided by the driver. So you know what to do when such a device is found. And when the device is detected now, so imagine it's done right now after all we have done. The first thing is that it will be the new device will be detected by the controller driver that knows how to detect a new device, like OHCI on the Atmel platforms. It will let the USB core know that some devices were found, and again, this is hardware dependent for the controller. The USB core will then look up the registered ID and find the matching driver. And the third step will be for USB core to invoke the probe method for the device, the one that was declared in the USB driver structure for the matching device driver. And this, of course, can happen multiple times if you have multiple devices. Yes, managed by the same driver or by different drivers. Of course, that's the way it works. And again, the good news is that this is really universal. All the buses are implemented using this technique. And what's nice is that this device model is actually recursive. So typically on a PC, for example, you have a PCI bus. And the first device you have on the PCI bus is the sound card driven exposing its functionality to user space through the ALSA, Advanced Linux Sound Architecture subsystem. Another USB device, PCI device, is actually a USB host controller. So here we see it first as a device driver, PCI device driver, but what it exposes is actually a USB adapter driver, which connects to the USB core, and on that USB core, then you have a network driver, USB network driver, that uses the network stack to expose its functionality. And then on USB, you can have a nice QWERTY adapter, USB S2C control adapter driver, a QWERTY adapter driver that's actually a USB device. So it has a USB device driver, but which implements a nice QWERTY controller adapter driver. And on top of that QWERTY, then you can have like small sensors like a thermometer, a temperature sensor, for example, for which you will implement a simple character driver. So you will implement a nice QWERTY device driver, but exposing a character driver to user space, like just the device you're reading, right? So you see here, even adapter drivers are device drivers at some point. Yes? Oh, want a mic?
When
Speak close to me.
yeah, when you when you insert a new device on that character device driver, is probe called on every single one?
And every single device, yes?
So like working down the chain on the rightmost kind of branch of that tree, you insert a new device. Does probe get called only on that highest most one, or does it probe get called on every single?
No, it's just per bus. So this here, if you insert like the USB 2I2C device dongle, it just happens at USB level. There's no need to propagate that.
Oh.
No, it's just per bus, per device on each bus.
So for any given plugging in something, you're only going to call one probe function.
Yeah, right.
Okay.
Unless, yeah, of course, here, if it's the USB to PCI and you can do PCI hot plugging, then you might have, like, if the device is already connected to that USB controller, you might have other probes that are called for devices that were connected to this one. So this, you could have more things. Depending on, remember, one probe for each device.
I'm just wondering, the adapter driver, is it just a protocol? Is it mainly just a protocol mapping kind of thing? So in this particular case, USB adapter driver, PCI, so is it just like converting PCI frames into USB frames, for instance? And also network drivers, are they just like pulling the networking, like the IP stuff out of the USB core, it knows where to get it kind of thing? Or is it more complicated than that?
It can be quite complicated though, because you have to, for a USB network driver, you have to do everything. You have to get data from the device, right? Write data to the device. So that's communicating with the device, but you also have to implement all the hooks that are required to manage the networking aspects. So you will have to implement a receive function and transmit function. You have to implement things like NAPI. So you everything you have something specific to each device. That complexity is reflected in driver, and Linux cannot really help with the device-specific things. So you have like some, the Linux kernel will extract as much as it can and provide services for people writing device drivers, but you still have like to handle the device-specific stuff, like to.
So it's just whatever you need to adapt what's coming off of USB core to a network stack. So it's just generic, whatever is needed.
So you'll ask the USB core for the interrupt number that the device will use. Then you can register that. Then you effectively can use USB to prepare to send the right control, the right commands to the device. So you'll use the bus infrastructure to that, and then back and forth. But that's it's not completely straightforward. It's not converting PCI to USB. You have different communication protocols to go through. Anything you want to say?
Oh, not at all. I was thinking you also have to deal with things like interfaces and what have you, going to multiple endpoints and what have you, in the sense that you can actually have a driver per set of endpoints that you've got connected up through a particular configuration. So in general, exactly what he's saying, but as he also said, it's more complicated than that too. It's we can only go so far down this rabbit hole.
Like a USB webcam typically has is actually exposing multiple devices, typically a button, an input device, video device, and also a microphone. Yeah. So it can actually expose multiple functionalities to different frameworks.
And actually, in some cases, a light as well.
Yeah. I hope this will become clearer by looking at some code typically also. There's another case, very frequent for us in the embedded world, is the case where you don't have, the devices you have cannot be automatically detected because they're just connected to the CPU on the system on chip. The system on chip is a CPU and a set of devices. You have, like, of course, internal buses to connect the CPU with the devices, but it's not something that allows hot plugging, always allows to detect the devices. One case is typically, yes, UARTs, for example, are directly connected to the CPU. Flash memory is like that, LEDs, GPIOs, MMCSD, Ethernet, typically all the devices you find on the Pocket Beagle or on the Cape will be like this. You don't have a way to detect them. Though you'd still like to use the device model because you can have like multiple devices of the same kind, multiple LEDs, multiple GPIOs, multiple buttons and things like that. So you still want to have this abstraction to manage multiple devices with the same driver and you use the same abstraction everywhere in the kernel. So the solution here is rather than relying on the bus infrastructure to detect the devices, you actually provide a description of the devices and then you have not exactly a fake bus from the software perspective, it's a normal bus. So the Linux kernel has introduced the platform bus, which is a special bus for such devices that are declared externally, not automatically detected. So that exists on the platform, pre-exist on the platform. And then you, with this, you can, thanks to this bus platform, you can implement the matching between the declared devices and drivers, and also get some attributes of the devices available on the platform. So we'll see how we can implement platform devices. So it's for devices that cannot be automatically detected by the buses. One case is typically I2C. There's each device on the bus has a unique number. Like an accelerometer will have like an address on the bus, 8-bit address. But you can't really know which, as it's only 8-bit or 7 bits, I'm not sure. You can't know which one it is. You can have like conflicts between devices that would have the same identifier. And therefore, the only thing you can do is scan the bus, talk to try each existing identifier and see whether there's a slave that replies. But you can't be sure which one it is, which one has this identifier. So you have to declare that externally. So to describe non-detectable devices, the first approach is to do that through what we call a device tree. And it's time to talk about the device tree that we started talking about yesterday. This is a solution that was implemented first on PowerPC and then later adopted on ARM and other architectures. The device tree descriptions are found on the ArchArm boot DTS, like device tree source. You have two parts for the device tree. You have the device tree source. There's one per board in the kernel sources, which makes the directory quite big. The advantage of having this device tree is that once you want to add a new board, all you have to do is create a new DTS file. And you don't have to recompile. Actually, this is stored in the kernel for sharing perspective, but this could be completely out of tree. Like you have your own DTS, you compile it with the device tree compiler, which is called DTC, provided by your distribution or provided by the kernel sources. And for a new device, you just describe the devices that are present on the board, and assuming your kernel already supports as modules for all the devices on your board, you don't have to go recompile the kernel. You just provide a new DTS, or actually you compile it to a device tree binary or blob, DTB. So you provide a compiled device tree, and the kernel can boot with that. So it knows what devices are present and what devices will match. Yes?
Could I go between two distros with a DTB file, and should the board just boot? I did something like this recently. I was trying to go from OpenWRT to Yocto. Would you need to recompile the DTS in that case?
Normally not. Or if you have the same kernel on both sides, that's okay. It will work. And then the DTB, the device tree binary, is supposed to be let's say backward compatible. And also the kernel is supposed to support all DTB. So you have an old DTB on one side an old kernel, but a more recent kernel on the other side with the other distribution. It is supposed to still be able to read the old DTB, as otherwise you're breaking binary compatibility if the newer kernel can live without the old DTB, with the old DTB. So normally, yes, you can actually use the DTB, for the same DTB for other operating systems that would support device tree as well. One case would be U-Boot. U-Boot is actually an operating system of its kind that needs a description. Oh, yes. I hope Marek agrees. I was saying that U-Boot is an operating system of a kind. Yeah, right. Thanks, Marek. So yes, this description is independent on the system, and any kernel should be able to interpret. What could go wrong, though, is that you have a very recent DTB compiled with some information, new information, and that's not supported by the old kernel that you had. So if you want to reuse the fresh DTB with an old kernel, it may not work. Yeah.
Oh, so yeah, going back in kernel version, it's definitely not supported.
Right. Wait for the mic.
Recently, I had an issue going from 4.4.9x to 4.4.110. So 90, something like that on a platform that I'm working on. So
right.
you know, I didn't know. I tried to drop my device tree from the .9 into the 110. So they made the changes for one of the MMC.
Was that 4.4 in both cases, or 4.9, 4.4 to 4.9?
I know that I was getting, from 4.9 to 110,
oh, yeah, right.
90.
Okay.
4.4.90 something to 4.4.110. I ran into an issue there, so just beware.
Oh yeah.
I was just going to say, the thing to understand is device tree is a moving target.
Right.
To a large degree, the only supported device tree for the Linux kernel right now is one generated by the same kernel. So strictly speaking, as much as it's supposed to work,
right.
A device tree should work with any kernel, and that's the ultimate goal.
But to be safe, it's best to recompile for the...
Yes. So unfortunately, it is not as finished as we would all hope. And that's going to take a lot longer, unfortunately, too. So yeah, basically don't use a DTB that wasn't generated with the same kernel.
To be on the safe side.
Indeed.
So so back to this DTB per board. That's very nice, because imagine it's distribution like Fedora, for example, that's targeting ARM. They want to support lots of devices, but they don't have the infrastructure like to ship a kernel for each existing device, like for phones or whatever. So it's nice because they can ship the same one kernel, one distribution, and it's up to the device makers just to provide their own write their own DTS, provide their DTB, add it to the image that's provided by the distribution, and there you are. The kernel, without any change, should be able to, of course, if it doesn't need any extra drivers, should be just able to boot fine on a new device. So there's no need to recompile the kernel, and you get the distribution updates as well from, like, typically Debian again. You can get the kernel updates, which will still work with your DTB. No problem. That's actually very nice. So you have it's very nice for distributions to be like in the PC world where all devices or all PCs were compatible. Here you can have one kernel for all, whatever they are, Freescale, Atmel or Microchip or whatever. And this is something not new in the ARM community, but like 10 years back or even less than that, we had like the kernel working for Freescale didn't work for Atmel, for example. So there's been some work to make this to have like a single kernel, whatever the SoC they can work on. So that's nice to have, because as a person making a new device, you may not even a new board, you may not even need to recompile the kernel. You can rely on whatever, for example, beaglebook.org is providing. Connect an I2C device to your board, add a device tree, change the device tree, or add an overlay to override the default device tree, and there you are. No need to recompile the kernel. So that's nice. So no need to recompile the kernel means that you can rely on others to publish kernel updates for security and things like that. So that's terrific. You don't have, like, whenever there's a security problem, a vulnerability, you don't have like to watch the news and rush to publish, to recompile the kernel and publish an update. If the devices can get the updates automatically, of course. So that's the first type, one DTS per board. And another type is device tree source includes, which actually allow to share definitions, like device definitions, typically between all the boards that share the same system on chip. Like all the AM335X baseboard, like BeagleBone, black, blue, green, pockets, they share the same SoC. So that's a way to declare all the on-chip devices for one SoC. And then the top-level device resources can include, the DTS includes, and actually enable the devices that they actually use at top level, because some devices may not be enabled or not be even exposed to the outside pins on the board. So that's a way to keep the DTS small enough. I will show some examples. Of course, there are other methods for describing non-detectable devices, like typically ACPI on x86. I'm lucky enough not to work on x86, so well, I don't know, but I only know about device tree. Sorry. But the mechanism should be similar. So let's take an example, a DTS site example. So first, let's declare an I2C controller device. It's the I2C controller is actually, you have like on AM335X that we have on Pocket Beagle. You have like 3 of them, if I understand correctly, like I2C 0, 1, 2, 3, 1, 2. So each device, it's a device connected to the SoC. So that's what you see in the DTSI for that chip, or even for that CPU family. So it starts with a top-level description somewhere. We don't have time to exhaustively cover device tree syntax, but there's a hierarchy here from a root node, and then some hierarchy of buses, internal buses that can be used to connect devices. In the case of OMAP or AM, it's OCP. It's an on-chip bus for connecting hardware blocks. So here, at somewhere in the DT side, you will have what is called a node, which is one device. Nodes are devices, typically. Not in all cases, but in that case, it's a device. So here you have like first a label that can be used to make a reference to that node later somewhere else. You have a node name that's usually bus type at address for the registers on the bus, the registers controlling that device on the bus. So that's here a memory mapped device here. So by writing to the corresponding offsets here, you can control the device driver for I2C 0, 1, 2 knows how to control the devices. The devices, the I2C controller devices on the system on chip. I'm not talking about the I2C devices yet. Compatible string is the compatible devices actually. Well, I should say devices. So it's a way to match between devices and drivers. So here, it's compatible drivers. So here it will match all the drivers. It will match the drivers that have this string. Address cells, size cells is information about the register, what the dimensions of the value that you have in the register, whether it's a single address or it's an address range. It's not the most important thing. We can skip that. That's information, that's properties for that device that the driver will the I2C driver we use. What's important here is status equal disabled. The device is present on the system on chip, but by default, it's not enabled. It's not used at the board level. So those are properties, yes. Reg is important because it corresponds to the register address, the address range for the registers to control that device. So that will be, of course, used by the I2C for OMAP device driver to drive the I2C0, I2C1, and I2C2 devices. And then, so that was the DTSI level for the chip. Yes?
When you say, yeah, cool. When you say that a hardware register, do you mean a hardware register like what you would find on a CPU, or do you mean like a separate memory address, like in RAM or something?
No. Well, it's part of the CPU address range, but corresponding to registers. So it's not RAM.
No, okay. I haven't done that much work with registers. Just so I understand, does every device have its own register, or is it just when it's being mounted?
When it's been?
Does each device have its own register permanently, or is that only when it's being like actually declared and registered? Does it?
Oh, it does have in hardware.
So registers are memory mapped from devices is the deal, right. As opposed to you're talking CPU registers versus hardware.
Yeah, sure.
Yeah. No, they're memory mapped.
For devices which are memory mapped.
Very true.
For devices which are behind the controller,
good point.
Then the registers for the controller are memory mapped, but not the devices themselves. Yeah, right.
Hold on.
Oh, you get that address from the data sheet. So the question was, how do you get that address here, reg? You get that from the typically the OMAP TRM. So you can. It's interesting because the OMAP TRM is a technical reference manual. Is a good document, for 5,000 pages. It's really nice, and it has all the information you need. So you can. It's nice actually to spend a little time to look. To find the same addresses, to find again the addresses that you have in the DTS or DTSI, mostly DTSI, to find them again in the OMAP TRM, because they are just the same. So you can this allows to understand what the drivers can do to use those registers, what the registers are, what the address range is. At least for OMAP, it's very nice to see the match between the datasheet. Oh, you got it, yes. That's for, yeah.
Yeah. If people want to see an example for TRM, we can show them one later. So that's.
Well, typically you have a base address, and then all the other registers are offsets. Like one register is 32-bit or 64-bit at that offset, and all devices of the same kind have the same offsets.
That might depend on the schematic or how it's been implemented on the board. Is this?
Yeah, go ahead.
I mean, this wouldn't be true always. It's only in this file that's been built, or this file's been created for a given platform or architecture.
For an SoC?
For an SoC. Like a different platform would have a different file entirely.
Of course, yeah.
Yeah. Okay.
So you essentially have one DTSI per SoC, and if SoCs from the same family share some common definitions, then they have their own DTSI to share the things that are in common between the two SoCs with the same family. So let's see what this definition, this I2C0 definition, is used at the board level. Typically when you create a new board. So here you actually use what we called yesterday a P handle. A P handle is a way to make a reference to this node that was declared in the DTSI and say you want to use it in your board. So here, the device tree language allows to add some definition to existing nodes. You just make a reference. You don't have to, some all poorly written DTS files still recall the hierarchy where, the location in the hierarchy where the I2C device was. But that's bad. It's much better to use an alias here, the P handle, and just to either add new properties or change the values of some properties. And exactly what we are doing here. For I2C0, we first add some pin maxing information that's important to enable the I2C level support, I2C0, sorry, at the electrical level. I'll get back to pin maxing in the next slides. Status equal OK is perhaps the most important one. It's actually enabling the device, the I2C0 device, so it's an SoC device on your board. Otherwise, it will just be ignored. Nothing will happen. That's for the controller, I2C0 controller.
So so the controller is disabled. So by saying OK at the device level, that's enough to turn the controller on. Okay.
Yeah. Well, then the probe will happen, and for the driver, for the I2C OMAP driver, the probe will happen. We don't see that when we implement an I2C device driver, but that's what happens too, in the same way for regular devices. True. And then you can also set some attributes that the I2C driver for OMAP will expect. Right, so setting the frequency. And then as children to the I2C0 node, you have all the I2C devices. So here, that's the bus. So it has you can have child nodes, which are actually the I2C devices that are connected on your board to that I2C0 controller. So and there's another one here. So there's one actually. The slides are slightly out of date if you don't take them from GitHub. So there was wrong definitions here. So this is the first device, second device. So an I2C EEPROM and TPS temperature sensor maybe. So they have a list of devices on this bus. So when you have a new device on I2C, you have to declare it in the device tree for your board. So yeah, typically when you want to use the Pocket Beagle, you do have and connect something quite trivial as an I2C device. You either have to use the user space abstraction to access I2C devices, like for Raspberry Pi, for example. As far as I understand, they don't ask for all the maker instructions and things like that when you connect a random device. All you have to do is just run some Python code that will talk to the device. That's true, but it goes through a user space mechanism, I2C dev, that allows to implement I2C drivers in user space. So that's nice, but the drivers are not generic. Yeah.
So when you plug, if you have this in the device tree and you plug something in.
Oh, wait.
So once you have this in the device tree, now you plug it in. Is there a probe function that gets called automatically?
Right. If you have like a matching driver with this compatible string, so matching happens with the compatible string. So if here in the device there's the compatible string matches a compatible string of a loaded driver, matching will happen, and the probe for that compatible string will get called. So in practice, if you want to use the kernel drivers, you have to use them. You have to declare the device in a DTS, in the board DTS. You will add the device to the I2C node, I2C0 in our case, with the right properties, the properties that the driver will expect, the driver for that device will expect. And the other thing I was talking about is doing without DTS, if you want. And that's what the Raspberry Pi folks are doing, typically doing everything in user space, using I2C dev. But the applications then working in user space are less portable. If you change the sensor, then you have to link against a completely different driver in user space. Actually, directly reading data and writing data to the device. It's less portable than the kernel approach, I believe. Though it's also possible, and I believe Michael will also speak about the user space interface for SPI. It's not always necessary to have to write a device tree to declare a new device. For buses like I2C and SPI, it's also possible to implement drivers in user space, though you might have like some differences in terms of performance. Now let's talk about pin multiplexing. Pin multiplexing is important for and that's another reason for creating a device tree for your new board. You know that modern SoCs have lots of on-chip devices, lots of them. Too many compared to, especially the OMAP ones, the AM1 OMAP ones. They have so many; they are quite big. It's possible to expose all the functionalities for those blocks simultaneously on the SoC. As a consequence, the pins have to be multiplexed. That like what we are doing here. And for OMAP, you have OMAP or AM chips. For the outside pins, you have to choose which functionality you want to expose, either GPIO, UART, SPI, or I2C. There's a table showing the possible combinations, the possible signals, internal signals that you can expose to the outside pins. And the pin configurations are defined in the device tree. And to make a device work, it's mandatory to have the right settings to enable the right signals. Otherwise, you won't get what you expect. Where are we in the slides? Yeah, I'll finish that. Let me show you the DT pin definitions. We'll take the example of the bone blue, which is in the mainline kernel. It's the same family of devices. So here you have, in the bone blue DTS, you have some pin muxing definitions for that particular, for I2C0. So here, essentially what it means is that you have a root node for I2C that will be interpreted by the pin control driver that's driving, that's interpreting the values and correctly setting the configuring pin multiplexing for that SoC. So essentially here, you say that if you want to have that signal, this signal actually on this C17 package pin, then you need to write to this offset. It's a register offset from the base offset of the pin control device, which is declared elsewhere in the device tree. You declare this pin as pull up or pull down, and then the modes is a way to declare like which pin. Like you have like 8 modes on a map, allowing to choose between 8 different signals. So you have like a table in the TRN that explains which mode allows to expose which pin. You also have other things to other values to control the drive strengths and things like that. So just 2 things. And when you instantiate the I2C0 device on the SoC, you will just turn it to OK. That's important because you use it. Set the frequency, but also make a reference to the pin configuration. That was here in another part. Here it's a child node to the pin maxing definitions. And here just make a reference to it. And if it's called, then there's pin control names, which will actually be a list of names. The first one will be for pin control 0. The second one will be for pin control 1. And if one of the configurations is called default, it will just be activated by default. The driver has nothing to do to select that configuration. So that would be the most frequent case, like 95% or 99% of the cases. And that's all you need to do this.
The pin muxing only happens at basically startup of your CPU and somebody initializes it. It's not dynamic. I mean, when you want to talk to the I2C, once the pins are assigned in your mux, they don't change.
I think it can be dynamic if you have a device tree overlays and things like that. That happens.
Yeah, it can change dynamically.
Mm-hmm.
Yeah. As long as your hardware supports it. Yeah.
Okay, quick question for you here. So, yeah. So earlier in your slides, when you're right here,
yes.
when you were
you.
searching the crowd. So when you were talking about the DTS file and the DTSI files, right? So the DTS file is one per board, and the DTSI are like fragments that are common to SoCs that I can include.
Exactly.
In, right. So let's say I'm going to make my own design using this, using the SIP that's on the BeagleBone Pocket. So I'm going to drop that on my own board. I'm going to put stuff on my I2C bus that's different than what's on this guy here.
Sure, yeah.
So does that mean I have to put that DTS definition in this directory and upstream it? I mean, you want all my customer boards, my custom boards showing up in that directory, or what's the practical way for customers that do their own design based on this to handle device tree?
I have no idea whether we're supposed to share the device tree sources or not.
Yeah, as far as I know, if it makes sense to upstream device tree changes, then perhaps set it up upstream. But having everybody's unobtainium boards configuration doesn't make a lot of sense. It was the same argument around board files. Do we set, do people send board files up into the kernel or not? I would say where it makes sense. But the thing is the device tree maintainers don't want to have 1,000 unmaintained device tree instances in there. But DTSI fragments, those. I mean, the ideal situation is where every part comes with a DTSI fragment. That would be from the manufacturer. That would be the ideal situation.
So my DTS file would be part of my application space, and I can run the device tree compiler, as long as I point to it, and so it doesn't need to be in the kernel tree then.
That's what I would do maybe for my own device.
So basically,
unless it's meant to be used by others.
Yeah, so keep it in my local copy of the kernel.
Yeah, local copy. So the big thing about device tree as well is there is an include for device tree, the /include/, but practically, and you'll see it even on Michael's slide there, everything in caps, those are actually CPP macros, and they're shared with the kernel. So if you extract from the kernel, you actually have to put all those in proper numbers. So within the kernel space, CPP is used because otherwise we'd all go insane trying to match up all the values.
That would be horrible. True. And this not putting code in the kernel, the mainline kernel, is maybe an exception, because for drivers, even if you're using something very specific, you think you're using something very specific to your need, it's always worth it to share with the community and have it in the mainline kernel.
Oh, yeah, totally agree with that. It's just that if I decide to hang device ABC off of my I2C bus, you don't care, right? I mean, no one else cares about that. That was my choice, but
drivers are almost always boring, and you might as well upstream them as a result.
So now matching, we get back to matching devices and drivers. So platform devices will be matched with platform drivers will be matched with platform devices that have the same compatible property. Like typically here in the driver, you declare the set of compatible strings that your driver supports. So you will support devices with TI OMAP4 I2C compatible property. And that's how you do in the driver. It's very similar again. It's a set of hooks like probe, remove, etc. Potentially power management hooks. Here, in that case, you don't have, or well, they are declared elsewhere actually. And reference to the set of properties here. OF means open firmware. That was the original name of the device tree back from the PowerPC times. And they haven't, it would be nice to rename that to DT to make things clear. But it still has the old name, open firmware. So OF means device tree. So now to use the platform bus, let's see some examples. So a probe example here, for example, OMAP I2C probe. So that's the driver. That's actually the driver for I2C0 that we've seen. So that's the driver for the I2C0, I2C1 and I2C2 controllers. we're using some infrastructure provided by the platform bus to access the device tree information, the device information. In the same way, we're using the USB bus to get information about the USB device or to communicate with the device. So here, for example, you can use platform get IRQ to get the IRQ number that was declared in the device tree. Platform get resource to get the base address, physical address for the registers controlling that device. So you get the address here automatically that was declared in right here. Get that address in the reg register so that the platform bus can access the device tree information. Well, this works whether you have the device tree or not. This uses the device tree when the platform has device tree. And then you can also read some properties here, the clock frequency. So it matches what we've seen before. We are accessing the properties from the device tree. And that's, of course, the driver needs that, of course, to operate the device. Device tree bindings, it's important to understand too. Device tree bindings are actually a specification of the properties that a driver expects in a device tree. The device tree bindings are available in documentation in the kernel sources, in documentation device tree bindings in the kernel sources. And I find this extremely useful to understand what properties you're supposed to set for devices, or to understand an existing DTS and figure out what the different properties mean. But as a user, when you instantiate a device, it's important to know what the driver will support. So for each driver, there's also a specification of the device tree property that it expects, and it's called device tree binding. So essentially what I do is when I have a new device, I want to understand first the matching driver and also the meaning of the properties. I do something like git grep. So grep if you have a git tree, looking for the compatible string in documentation device tree bindings, and you have a nice specification. I could show you one, yeah. Now, because these are not real codes. And a cool thing, by the way, that I like very much is with git grep is -o and the editor of your choice. This directly goes to open an editor with all the matching, all the files that match the search. You directly are in the right location in the resulting file. So that's very convenient. When you have a set of matching files, you don't have to run the same query on all of the matching files. So here, that's the binding for OMAP, for that driver, I2C for OMAP platforms. You can see the possible properties that the driver supports and the meaning of the properties, the optional ones, etc., and some examples as well. So the bindings are very useful pieces of information to understand what a driver expects and what you should put in your devices. And then you can look for, by using git grep as well, look for the matching drivers, like that property in the drivers subdirectory of the kernel sources. And you'll find the matching drivers too. But it's often sufficient to start with to use the device tree binding information. You don't have to look at the source code for the driver to know how that information will be used. And now it's time to talk about the I2C bus. A commonly used low-speed bus to connect on board and external devices to the CPU. 2 wires, SDA for the data, SCL for the clock. It's a master-slave bus. So only the master can start transactions. and the slaves can only reply to transactions that were initiated by by the masters. So typically on Linux, the I2C controller is actually the master is the controller on the I2C, controlling the bus. It's now possible to have Linux running on a slave device, but that's less frequent. Like if you have like, the slave is actually a Linux device, that's possible. Each slave device is associated to a unique I2C address. And effectively, the device uses the address to recognize the messages that are sent by the master. So it looks like this. An I2C controller, you can have like multiple devices. There's a limit to the number of devices you can have. There's too much load on the bus, then you'll have some electrical problems. So maybe 10 or something is a realistic maximum. The constraint of the I2C bus is that you can't have 2 devices with the same register here. Like for example, if you're using Nintendo nunchucks, nice input devices, you can have 2 on the same bus. But fortunately on a map, like you have 3 I2C buses. So you can put them on different buses or use expanders maybe. So that's still a possibility. But since this address has to be unique on a given bus, and usually it's hard-coded on the device. Now let's look at the probe function and explain. I hope you can read, otherwise open the slides from the website. So cmeale.org. The probe is going to be called every time there's a matching device that is found. And it always has the same prototype. The first parameter that is called by the kernel is a pointer to a client structure. A client structure is actually the instantiation of the device structure for I2C. So every time a new device is detected, the kernel will allocate a client structure. And that's used to communicate with the device for all I2C operations. Another aspect is that I'm going to give the example of an accelerometer, and this accelerometer will actually expose its functionality through the IIO subsystem. And IIO is typically for industrial I/O devices. So there's a framework to consume data from IIO type of devices. So here, that's what we're going to use IIO to expose the function, to let the user space access the accelerometer functionality. So therefore, we have to declare a framework structure, and that's important because we haven't really detailed it when we were talking about the device model, because we were talking about the bus aspect. Now we are going to start a little bit to talk about the framework aspect. So here, we declare a structure for each device that will be used to expose the functionality of that device. We also have a per device structure here, this pointer actually, that contains some information that the driver will use for each device, like per device lock, per device wait queues, per device, whatever you need to manage the device and the driver. The first thing you do here is to allocate you allocate the framework structure. Oops, there's no comma. So it's and this is the same for all frameworks. You allocate a structure for that framework, so it's called IIO device alloc. DevM is a special set of functions. I'm not sure we have time to cover them in other places in the course. DevM means device manage. So this allocation is going to be associated with that device. So this is going to allocate memory actually for the IIO subsystem, containing some space for the data. It's a private structure. It's actually a pointer that you can free that it's a part of the structure actually, sorry, that can be of a specified size so that you can embed your per device information for the driver inside the framework structure. So containing your own stuff as many as you want, like again, log queues, logs, wait queues, etc. Reference counts, and I mean counting the number of bytes, for example, if you want. So we allocate the structure. With DevM, it's nice because when the device is removed or when the driver is removed, the device will be removed actually, and automatically this allocation will be freed. So actually, the allocation is actually associated to the client here, or to the device structure in client. So, what I mean here is that when the device is removed, or when the driver is removed, this will be automatically garbage collected. And this simplifies the subsequent code here. If you have a failure somewhere registering the IAO device, for example, you don't have like to undo everything that you did before, run IAO free device, etc. Or just use K3 maybe if it's possible. You don't have to do that. It's automatically garbage collected. When you exit probe with a failure, then the device will be destroyed, and before destroying the device, all the associated devm allocations will be removed. So you will see in the kernel code lots of devm statements, like devm request IRQ, devm alloc something. All those things are undone automatically when the device is removed or when the driver is removed. So that's very nice because it simplifies error codes, it simplifies remove functions because there's a lot of automatic garbage collecting that's done, and that's super nice. So here, let's continue a little bit. We declare data, so it's a structure containing our own stuff for the driver. It's the private part of the IAO structure. So we get a pointer to it for our convenience. In data, then we can have a reference to, we store a reference to the I2C client. So practically, we have a link between the IAO structure and the framework structure, which is the I2C. So every time there's an IAO event that causes us to write to the device, for example, we have that information. So we can write to the device. And the opposite is I2C set client data. We can attach the framework structure to the bus structure. So that, for example, at remove time, when the device is removed, we know which, for that device, we know which IAO structure we have to remove. So we have to do this because one driver can support multiple devices. So that's why you have to store pointers back and forth. If you just had one driver and one device, you could manage that by like global variables, and it would be enough. But here, that's why you need some structures because, yeah, you manage multiple devices. You enable the, so here we prepare the device too. So we do some I2C reading and writing by using a function that you could have a look at its code. And once the device is ready, you do IAO device register to declare the new IAO device in the system when everything is ready to be used. And if it fails, the registration failed because maybe that it was already present or there's a conflict with something else, then you can react to that and you return the return value. So it's a 0 success again, if you remember, or the actual cause for the error which was returned here in case something failed. I hope we are seeing remove, and that's important. So remove is going to be invoked when the device is removed. So here you'll be using I2C get client data to retrieve the pointer that we stored in set client data. So here we attached to client, there's a private data structure that keeps track of a pointer that you want. Here we used, of course, the pointer to the framework structure, the IO structure. So of course, before, at remove time, when the device is removed, we of course have to unregister the device, but we need to know which one. And that's why we need the pointer in the client. In each device, we need the pointer to what we allocated before, to the what we registered. So thanks to those links, those references, we can unregister the right framework device, the right IO device. Yes?
So is the reason that the init and the remove, or the probe and the remove, are being called with the I2C client? Like, what's the relationship between this driver and I2C? Is it solely because of the device tree, in that it's like a sub module of the device tree I2C?
Well, it's just that at remove time, you know what device gets removed, so you invoke the remove function from the matching driver. So,
like, I guess what makes MMA 7660 use I2C client versus just being a different sort of probe? Because obviously there's if this was a SPI device, then I'm sure it wouldn't be I2C. It would be
that's this part actually. The next slide.
Oh, okay.
It's so effectively you register probe and remove here to I2C using module I2C driver. So that's the macro that's going to create the init and exit functions effectively. Yes, yes. I should have. It would be a good idea to show this first and then probe afterwards. I could reverse the order. At the end, here, once the user space can't access the device anymore, you can disable the device. Don't switch those lines. You should disable the device too early. You may still get some requests from user space and have a race condition. So do this only when the unregister has been done. And this is the same everywhere. That's the good news. So to register the device, yes. So to register the device, you are going to use some device tree statements to declare the matching compatible strings that you support. It can be a list. Another thing you have to do in I2C, I'm not completely sure why, but you also have to match by name. I mean, the name information is essential in I2C. You have to have a matching name somewhere. I mean, you have to have that name information. Otherwise, the device tree matching only doesn't work. Even if you're just using the device tree, you're not supporting platforms that don't have the device tree, like PC. If you don't put that name information, this part here, I2C device ID, from my experience at least, the device tree information is not sufficient for matching to happen. This is not the case with UARTs, for example, with other subsystems, but with other buses, sorry. But for this one, for I2C, that's you have to put it. So here you have a reference to a list of compatible strings. That's the equivalent of the USB product ID and vendor IDs. And this is sufficient to make the matching work. And as this device supports also ACPI-based devices, there's also ACPI information that's available. And then to communicate with I2C, and then I'm done. You can have, it's nice to start with I2C, for example, maybe SPI, because once you have a client structure, you have nothing else to explain. Like, we don't have to write registers and explain how to map the registers, the memory-based registers, memory map registers. All you have to do is just use functions like I2C master send, I2C master receive, the I2C client that's passed by the probe, and all is taken care of by the I2C control drivers. So quickly you can quickly read and write to a device without having too many explanations about kernel programming, about memory access and things like that. There's another API that you could use, and I believe the driver that I showed you is using this one, is the Sms Bus API, which allows to read and read byte data, write byte data. You can do more a little more complex commands that then read and write at the same time, typically. So you could use those, and what the kernel documentation recommends is to actually use this one, because there are some buses that support the SM bus, but don't support the full of I2C, which is a superset of I2C. Yes, of SM bus. So driver development advice to understand existing code. Look for code for devices similar to yours. You'll find useful information. The kernel documentation is not so great everywhere, but what saves us is that you have lots of examples, working examples. You can read the code. You can use what we have, like at Bootlin, we have ELXR, which is a way to index the kernel sources online. Like you can look for function definition, see where it's defined. Look at the code, and then follow some links, make some further searches like this. So explaining for each identifier where it's defined, where it's referenced. So where it's defined, where it's implemented, and where it's referenced. So you can have plenty of examples. You can browse the source code this way. That's quite convenient tool for exploring the Linux kernel sources, and it indexes all the versions that are known to Git. And we also support other projects now. We are progressively expanding it to support BusyBox and others. And another way of doing things is always start reading the code from the bottom, because that's where the top level definitions are. And then progressively go up to the top. Like first you read the driver definition, the driver structure definitions. Then you can read probe. And then after in probe, you can see some functions that get called or some things that get declared. You see, and you can read the code for those, progressively going from the bottom to the top of the driver source. That's the natural way to understand some code. Further reading about device tree. We have, like at Bootlin, we have a complete five-day course for kernel development, which has more details about various subsystems, kernel debugging, and things like that. Everything is available under a similar license. There's also the presentation from my colleague Thomas Petazzoni on a specification of the device tree language, how it's used on ARM. And there's the kernel documentation I2C that's valuable as well. In there, describing the various functions, the various APIs, how you're supposed to use I2C. So, sorry, it took a bit more time than expected. I could quickly show you what we have in lab directory, so that you know what it is and you can try by yourself. Do we have time to run the labs or just demo the labs, right?
It's a good idea.
Just run them. Yeah. So if you connect your board under code resources, if you connect the USB flash drive that you have and mount it, you have a nice resource. You have a resource directory, a resources directory, and then a nice driver directory that allows to demonstrate how to access the accelerometer on that device. So thanks to Michael Welling for preparing this part. Sorry.
We're just demoing the platform registration in a few forms. So the first one is going to show you how to do it from user space instantiation. That's what this echo foo into sys I2C device is. So we have a very simple driver that has a device table in it, and it you'll see if you look in the lab1.c.
Yep.
So
I
if
can
you
do
open
that.
that up, you'll see some very basic driver that it only has a probe and a remove function.
So here we actually instantiate a fake device on the I2C bus.
Yeah, and we're actually associating it with
A name.
the accelerometer that's on the board, so that it'll actually probe. Otherwise, it just won't work. But
so it's matching by name here.
Yeah. Yes, we're matching by.
Not device tree.
Yeah, not device tree yet.
Yet, right.
So if you just run make.
You see, so
yeah.
That's the device name and
the address.
And address.
That 1C is the I2C device address, and that's the first byte that it sends through I2C. Has that. It has like the address, read-write bit, and some condition like start conditions. It's all part of the protocol.
Make already compiled actually.
Yeah. It'll compile both of them at the same time.
That's true.
And then.
So should I?
Yeah.
First?
You're gonna have to sudo insmod.
Oh sure, of course.
No, it's just a very basic driver just to show the probe functions because we didn't have. I don't think we had enough time to go through a whole driver. So what I did in the previous session is I actually opened up the IIO driver and then I showed you the various pieces, and we can do that as well if we have time. So once you probe or you force the module, you load the module, it'll show up in ls mod.
And you can see the messages.
Of course. Then you got, oh, yes.
Oh, yes.
when you create your own module out of tree, this message will come up. Don't worry about it. It's just, they rather you not use out of tree drivers, but yeah.
Although we don't see the PR info.
Well, it's because we haven't probed it yet. So you have.
Oh, right. Sure. Yes, you're right.
So when you echo into the it'll actually, it's in the README.
Yep, sorry.
If you echo that string into that sys bus devices I2C, this is documented in the I2C documentation as one of the forms of instantiating devices. It doesn't work for all devices, by the way, because some drivers are actually associated with multiple hardware, and it gets a little sticky when you do that. So.
Paste didn't work.
Yeah, you gotta probably cat it again or VI again. Yeah. So once you do that echo. Why didn't it copy?
That's weird. The terminal can be weird. Sorry.
Yes. So yeah, when you run that and then do a demessage again,
yep,
you'll see, oh, look at there, new
devices
is called. So that's the very basic foundation. So you now can start into your I2C driver essentially. Now, if you're using an ARM target, you're probably going to want to use device tree. So we're going to, for the second lab, we augmented that driver with I2C using device tree
bindings. So that's what we declare.
Yeah. Say, some of this code is actually copied right out of the documentation. But the compatible string is what matches with the device tree. So
it's product and vendor.
Yeah. It usually it's
sorry, vendor product.
Vendor product.
Sorry.
Yeah. So it'd be like if it was the accelerometer on our device. I think it's Freescale maybe Freescale, and then after the comments got the device is MMA 4084 something. But we can see that we're actually going to probe that module in a minute here. But this compatible string will be matched when we do a device tree overlay, which I don't know if you guys, do we talk about the overlays?
No, not yet.
Okay, well.
We can say a few words.
Yeah, you can show them, I guess.
Yeah, the overlay.
The device tree overlay file.
So it was lamp2.ts, right?
It's actually, it's called, I don't remember what it's called, do it ls. I2C foo. Okay. So yeah, he mentioned the pin muxing. So instead of having a whole DTS file, you just take and overlay with small fragments of the device tree.
So that you don't have to reboot.
Yeah. So when there's a couple of methods, but the mainline way of doing this now is using config.fs, and you select the I2C target, and then you overlay the struct that's in the top level or subsequent levels of DTS-I. So this is the I2C2 controller inside. So that would be what we're going to overlay essentially. And up here, these pin muxing you can ignore those. This is BeagleBone kind of specifics. They have this pin muxing that they use to toggle the pin muxing in the user space. It's a utility called config pin, which allows you to change the muxing.
That Jason showed yesterday.
Yeah. So I think he's just disabling that so that we don't override the pins. And you see again that the one Charlie is there, the address. Yeah.
And then, oh yes, that's the DS. Do you want to see the driver again, or shall we run it?
You guys have the copy of the driver source. Let's try getting loading the
module first.
Loading the kernel. We've already
module, yeah.
Module, yeah. So it's kind of I kind of wanted to build upon the platform registration or instantiation methods, and then maybe get a few access methods. The second lab does actually access the hardware. You'll see in the code.
So I can show.
It reads an ID from one of the registers. That was just to show the drivers essentially, or the scripts. So
the way to compile the device tree overlay.
Yes. So this is a magical script to do the device tree compile. So that'll take the DTS, the file, and create a DTBO, which is a device tree overlay, and then it's going to pipe it in through the config.fs.
Right. The next
yeah,
one.
and we already looked at the DTS, so we could just run that script, and then you'll see.
Prop code.
See what happens is we didn't remove the module previously, so that's a dual registration. So you'll have to rm mod the lab1, and you'll probably have to delete the device, which is also in the instructions.
Okay.
It's built right into the kernel. We can bring it up for you, or you could just go to the Elixir or clone the kernel source and see it. It's mainline. Once you get this demo through, we can pull up the code for that, so we can check it out. There it is.
Right.
I don't know why it's
probe
failing.
code.
The probe was well, it got through the probe.
Yeah.
Because it's got the I2C read, but the
okay.
bus is a little confused, probably because of what
maybe a wrong return value.
Yeah. Well, I think it's supposed to only return an error if it's negative. This only happens if you don't remove the device because the registration kind of gets messed up and you have to reboot. But that SM bus read
that's probably the part that failed.
Is working. Yeah. Well, it shouldn't have because it's not less than 0, right? Okay. I guess we don't have a whole lot of time. I can show everybody where the device driver's at. But the last thing is actually loading that accelerometer driver finally. But we have to make sure we remove the module and the
device.
And the device from config.fs.
Well, I copy all this.
Yeah, let's do them both. There we go.
Oh, sorry. Oops.
All right, and then we got this last piece just launches the accelerometer driver, and then it shows the accelerometer running essentially.
I'll do the cat at the same time.
We'll see. We'll see if it works.
And
it's
then
got a 2-second delay, and it didn't work. Now, if you press Control C now and do a D message, you'll probably see the same message you had earlier.
Yeah.
So you're going to have to reboot the target. Okay. And
Sure.
then you should be able to launch the accelerometer driver.
You press reset. Thanks.
If you press reset, he's SSH'd in. It's gonna.
That's okay. I'll get back.
Yeah. Demos always end up with hiccups. If you don't do the exact steps, you run into problems sometimes. Or sometimes the exact steps are wrong. I think it might be a little out of order on the README. I just kind of pasted those
Hey,
together.
back?
Yeah, no, it's perfect. Oh, yeah.
Yeah, usually you only probe one driver on a specific address. You don't keep.
All right, cool.
Interesting. Interesting. What does it say in your kernel messages if you do a D message? D message, DMESG. That's all it says. Okay, then it should be there. Oh, that's because it's device 0 because we haven't loaded the potentiometer.
Then you.
Yeah, it's probably doing the same thing on yours. Close out of it and open the script.
Is that lab3.sh?
No, it's I don't remember what it's called. It's something .sh.
Oh yeah.
Accelerometer, and it's got right here. This should be device 1 because it's the only one on the bus. There.
Oh, you know what? Get rid of the backslash and the double quotes. I probably broke it. Sorry. Yeah, get rid of the backslash.
And you'll have to switch device to device 0. Is it working now for you? There you go.
Yeah. Okay.
Magic. So now
I'll
if
fix
you
it.
move the device
Thanks.
around, it'll actually start giving a reading. And I think in the other at the other conference, I demonstrated accessing this with raw I2C character device, which was a little different. But yeah, that's it. That's I2C for you.
Yeah, take your time to look at the real driver for this. It's
Yeah, it's similar to the driver you
Right,
showed in the slides,
exactly.
but you'll see how it correlates to the hardware. And we couldn't write a whole driver in the course of the class, so we used
the first thing you could do is actually do some I2C reading in probe, for example.
Mm-hmm. We did that one. We did one read in the probe, and that that showed like reading of the who am I register inside of the device.
Oh yes, true.
Yeah. So.
Sadly, we run out of time. If you want to ask further questions, both of the Michaels will be available between during the break. That's right. Well, and then the other Michael will take over. It's the afternoon of the Michaels. But thank you very much, Michael.
I know, the morning too.
That's true. This
Michael
morning
Anderson.
we had actually it's the day of Mike's because Michaels because Mike this morning is true.
Yes, sure.
Yes. So,
yes,
but thank you very much to Michael Opdenacker for the talk. And
thanks, Michael.
Michael Welling also for the labs. Thank you very much.